So today we're going to start lesson 5.4 notes. Remember for tonight, do lesson 5.3 homework, and that'll put us on track there. So lesson 5.3, you learned about first derivative test. We're going to spend lesson 4 talking about the second derivative test and talk more about concavity, which I know we talked about a little bit yesterday. So in our last lesson, we found intervals on which a function was increasing or decreasing and discovered how the first derivative test describes the direction of the function, or in other words, how the y values are changing. In this lesson, we see that the derivative of f of x, the second derivative, will describe the concavity. Concavity tells us the direction of the curve or how it bends. Just like direction, concavity of a curve can change too, and the points of change are called inflection points. Now, as we look at concavity here, it suggests that we draw small tangent lines at points along the curves below. And so the idea when we talk about small tangent lines, a tangent line there, a tangent line there, tangent line there, and a tangent line there. Okay? And the idea is, well, what they ask us is, what do you notice about the slopes of the tangent lines, or in other words, the derivatives, as you move from left to right at these points? And so, as we look at all these tangent lines, each time as we move from left to right in this particular one, our derivatives are increasing. So the idea that the slopes of those tangent lines are going to be increasing each time or getting more. So the idea here that in this scenario, the derivative, f prime, is increasing. Now, if f prime is increasing, how that relates here is that this is what we call concave up. Yesterday when I tried to talk about concave up, I talked about it being bold up. Okay, but anytime that as you move from left to right, your derivative is increasing, that's going to be concave up. In this scenario, notice the tangent lines that I just drew, they all lie below the graph. Okay. Over here, if we put these same similar tangent lines on, okay, each time we are drawing those tangent lines, technically the slopes are getting smaller. And so we can talk about the fact that f prime is decreasing. And if your derivative is decreasing, that is an indication of concave down. Again, yesterday I described it as being bold down. And in this scenario, you'll notice that the tangent lines of all of these laid above the graph of f. Okay, so in a concave up scenario, your tangent lines are going to lie outside or below the graph. If you're concave down, your tangent lines are going to lie above the graph. In terms of concavity definition here, kind of what we just talked about, but let f be differentiable on an open interval. The graph of f is concave up if the derivative is increasing on the interval, and it's going to be concave down if the derivative is decreasing. Okay? And so this is where the second derivative comes into play, because in order to know if the derivative is increasing or decreasing, we can look at the second derivative. If the second derivative is greater than 0, or in other words, positive, that means the first derivative is increasing, and thus my graph is concave up. Or if the second derivative is less than 0, or in other words, negative. Well, if you have a negative second derivative, it means my first derivative is decreasing, and thus my graph is concave down. Okay, so first derivative being positive or negative tells me if my original graph is increasing or decreasing. Second derivative tells me if my original graph is concave up or down. Okay, so let's go look at an example of how we apply this. Given f of x is this 1/3 x cubed minus x, they ask us to determine the open intervals on which the graph is concave up or down and state the point of inflection and explain how you know. Okay, so several things that they ask us to talk about. First of all, anytime I see concavity and point of inflection, I'm going to go for second derivative. I know I'm going to have to talk about second derivative there. So, what is my first derivative?
X squared minus 1.
Okay. And then first derivative is x squared minus 1. What is the second derivative? 2x. Okay. So, at this point, in order to find critical values, okay, we're going to set our second derivative equal to 0, similar to what we did with critical values for the first derivative. So if you set 2x equal to 0, x equals 0, so that is a critical value of the second derivative, and it is not guaranteed, but it is very possible a point of inflection. And what they call POI is point of inflection. And that's what we're going to be checking here, is we're going to be figuring out, is that a point of inflection? If it's a point of inflection, what that means is the concavity changes at this point. So just like yesterday in the first derivative test, how we set up that number line, we can do the same thing here. I'm going to set up a number line. This is for my second derivative. My only critical point there I have is 0. And just like first derivative, we're going to test it. So pick a number left of 0. So for instance, if I test x equals negative 1, and we're going to put x equals negative 1 into the second derivative. So we're going to put it in right here. If we put in negative 1, 2 times negative 1 is going to result in a negative. Okay? That means a decreasing first derivative, or more importantly, it means concave down. Okay? I use CD to represent concave down. So that means this piece of the graph will be concave down. If I test a number to the right of 0, say 1, 2 times 1 is going to be positive. And that means this portion of the graph, since the second derivative is positive, is going to be concave up. Based on the fact that to the left of 0 is concave down, and to the right of the 0 is concave up, what does that mean must occur at 0? That is a point of inflection. Okay? Now, so, facts to write down. They asked about concavity, on which intervals the graph is concave up or concave down. Okay, I'm going to refer to the graph as f of x. F of x is concave down. And what interval is it concave down on?
Negative infinity to 0.
Negative infinity to 0. And I'm just using a parenthesis because at 0 it's not considered concave up or concave down. And why is that? Why is it concave down? And that's because the second derivative, f double prime of x, is less than 0. So the official mathematical way to say the second derivative is negative. We can do a similar statement for concave up. F of x is concave up on the interval 0 to infinity. And that is because second derivative is greater than 0. We also need to talk about the point of inflection and explain how you know. There's a point of inflection at 0, and the reason we know is because we could say the concavity changes, but concavity changes because the second derivative changes from negative to positive. So that's the third piece I'm going to mention, is that f of x has a point of inflection at x equals 0, since f double prime of x changes from negative to positive here. Okay. Okay, so that's just a little bit about what the second derivative tells us. Okay. Next. Okay. Example 2. First of all, do note that equation is familiar, right? This is the example from above. But what we're going to look at here is basically the graphs of each of these and how the derivatives go together with them. The concavity, so the second derivative, and direction, the first derivative of the function, is related to the slope of the derivative. And what we know here. Okay, let's see. I'm going to back us up a moment because, well, before we proceed too far, in order to help us talk about and debating what order I want to do this in. Okay, let's take, so up above, we took the second derivative, set equal to 0. We found our inflection point. Okay, I also want to take our first derivative, and because we didn't have to do this up above, but if we take our first derivative and set equal to 0 and find some critical points. So if I say x squared minus 1 equals 0, then what? We know x squared equals 1 and x is plus or minus 1. Okay. Remember, since these are places my first derivative equals 0, these are critical points. On the graph, what are they most likely going to be?
Arrows. Or extrema.
Extrema, right? So these are going to be your mins and maxes most likely. Okay. I won't ever say guaranteed, but, you know, That's what should end up happening. Now, as we look here, okay, I think I'm going to have us graph the second derivative first. The second derivative, that's not the second derivative, that's the first derivative. That's what I'm pointing at. F prime of x equals x squared minus 1. So what's that graph look like? X squared minus 1 is a parabola that is down 1, yes? Now, think about the pieces here. We know this graph is going to cross the x-axis at 1 and at -1, which are the critical points we just came up with, right? With that in mind, what's going to be a min and what's going to be a max? That's what I'm trying to get us to, I guess. My first derivative is what? Up here it is positive. Between -1 and 1 it is negative. And to the right of 1 it is positive. So if my derivative goes from positive to negative at -1, what's that going to make it? Is this the easiest way to...
Point of inflection.
I'm sorry, what'd you say?
A point of inflection.
Well, remember we're talking first derivative here. This is our first derivative. It's my first derivative. It goes from positive to negative. That means, what does that mean my original graph is doing? My original graph is then going from increasing to decreasing. So if my original graph is going from increasing or decreasing, what does that mean there's going to be at -1? Extrema, specifically a maximum, because it's going from increasing and decreasing. Whereas over here, at -1, or excuse me, at +1, my graph goes from negative, so it goes from decreasing to positive increasing. What's that mean it's going to be at 1? That's going to be a minimum. Okay, these are the type of things that my graph can tell me. Okay. The other thing we can talk about right here, if this is my first derivative, something that we'll be able to talk about right here is a minimum on my first derivative means that's going to be someplace where my second derivative equals 0, because there would be a horizontal slope there. Okay. Now, I put f double prime of x. I think really what I should put there, because that's going to be happening at 0. Okay. Should have thought about better how to do this. Okay. Okay. Let's go back to the first graph now. We have some information up here, and that we know it's a cubic, right? We know the basic cubic. I mean, a basic cubic with no other pieces is like that. When we throw in the other pieces, we're now looking at something doing like that. Okay? Now, what did we already know? We already knew we have critical points from the first derivative at -1 and 1. And then, if you look back up above, there was a critical point of some type of a 0 there, at 0, because of the point of inflection. Okay? I'm not liking how this is working out.
Teachers, pardon the interruption, but I need the following students to come down to the main high school office. Layla Baldwin, Logan Creason, Gavin Landrum, Jaden Moretti, Lucas Moss, Brendan Philippi, Laney Prater, Aiden Rummel, Christopher Sluka, Lindsay Walker, Josiah Pierce, Braden Hook. Please come down to the high school office. Thank you.
Yeah, it's something vocational related. Okay. What did we already decide? Blah, blah, blah. Okay. We know at -1, we talked about there's going to be a max. And at 1, we talked about there's going to be a min. We talked about there being a point of inflection at 0. Not that it necessarily has to be at that 0, but there's a point of inflection at 0. With that in mind, and you know what I'm realizing? I'm trying to make this too much into curve sketching. We do curve sketching later. That's what I'm trying to make this too much into. Okay. So I'm going to put it more together here because in my brain, I'm thinking we need to be putting all the pieces together. I'm just supposed to be showing the connections here. That's what I'm realizing. Sorry. Okay. So at -1, we said there's going to be a max of some sort. Okay. At 1, we said there's going to be a min. And then if you do the math at 0, it has to cross through 0. We have a graph that looks something like that. Not exactly my best shape, but notice the pieces that all go together. There's a max here. We knew that from looking at our first derivative. There's a min here. We knew that from looking at our first derivative. At 0 here, there is a point of inflection. The point of inflection changed from concavity, we knew from looking at our second derivative. Okay. Now, the summary they have down here is, okay, so first derivative, my critical points were -1 and 1. And if we look at each of those, to the left of -1, my derivative would be positive, because that's an increasing graph. Between -1 and 1, my derivative would be negative, because that's a decreasing graph. And to the right of 1, my graph is increasing, so that would be a positive derivative there. So the idea that this is increasing, decreasing, increasing. On the second derivative, our critical point was 0, and this is what we already did up above, that we came up with the left being concave down and the right being concave up. Okay, and still using those symbols that I believe were introduced to you yesterday in the second half of notes.
Yeah.
Okay, am I right on that? They were introduced yesterday?
Yeah.
Okay. I didn't get very far. I wanted to get farther than that. Maybe, just maybe tomorrow we can have a full day. Okay. On the next page, I don't know if I have enough time to talk about this or not. It talks about the definition of the point of inflection. Thank you, girls. And the point of inflection is, we already talked about, the concavity changes from to up or down to up. That is your point of inflection. Notice here's a big thing. If the second derivative is 0, which we've already talked about, or if the second derivative is undefined. Just like with that first derivative. If it's 0 or undefined. Those hit key points there. Now, inflection points. Okay? There's an inflection point right here. Notice it changes from concave up to concave down. Okay, so there's an example of an inflection point. In this case, well, I don't know if I'm going to have time. I'm not going to have time to put the labeling on it. Here, we have an example of an inflection point because it's concave down to concave up. And then over here, we have an example of an inflection point. And again, concave up to concave down. Okay. The thing is here, your second derivative on this one would be an example of a D&E, where it wouldn't exist. In this middle one, your second derivative would be equal to 0. Okay? And this would be a one where it'd just be your second derivative would be equal to 0. Okay? We'll pick up in 5.4 notes tomorrow. Finish the 5.3 homework tonight.